This video is sponsored by Let's Get Rusty. Have you ever wondered how the Java compiler can be written in Java, the C compiler in C, and the Rust compiler in Rust? I mean, how can you compile the compiler if you don't have a compiler in the first place? Hi, and welcome to Premature Abstraction. This is the first video in a series where you learn all about compilers, one of the oldest and still most important topics in computer science. The goal is that, by the end, you'll even be able to write one yourself. So please subscribe if you don't want to miss that. In this video, I will give you an overview of what a compiler is, what it does, and answer the question from the intro: how a compiler can be written in the same language it compiles. In a very general sense, a compiler is just a program that translates an input from a source language to a target language. Most of the time, when we talk about compilers, the source language is some kind of higher-level programming language like C, and the target language is some form of machine language that can be executed, like x86 assembly. It is important though to understand that this is not inherently the case. The target language can also be just another programming language, which makes it what's called a transpiler. A well-known example is the TypeScript compiler, which compiles to JavaScript. Or something completely different like VHDL, which translates a hardware description into an FPGA configuration. Or a LaTeX compiler, which outputs a PDF file. Or even a decompiler, which translates from machine code back into a higher-level language. Even DNA in an organism can be thought of as a program that is compiled by the cells into executable proteins. But since compiling programming languages into machine code is the most common use case, we'll stick with that for now. When the code is subsequently run, it takes an input and produces an output. There are also programs closely related to compilers called interpreters. They do both in one step. They take the source program and the input, often interactively line by line, and directly produce the output, without necessarily generating a separate executable first. There are even hybrid approaches like Java. Here the compiler compiles the source program into an intermediate language called Java bytecode. That bytecode is then run on the Java virtual machine, which executes it with some input to produce the output. So it's a combination of a compiler and an interpreter. In this series, we will focus on building a compiler simply because topics that matter for good interpreter design, like just-in-time compilation, are extensive enough for their own series. Currently, one of the most exciting developments in the compiler space is the Rust language. That's why I'm delighted to have Let's Get Rusty sponsoring today's video. If you're a developer, you've probably heard Rust mentioned a lot lately, and for good reason. Companies like AWS, Microsoft and Google have been heavily investing in Rust for performance and safety-critical code. So if you want to get paid to build fast and reliable software, whether that's backend infrastructure, robotics or even blockchain, Rust is a great language to have in your toolkit. Let's Get Rusty offers Rust training for individuals and teams, with a big focus on practical skills and helping people move into Rust roles. They have already had thousands of devs master Rust. The best part is that they've got a new cohort starting next month already, and spots are limited. So if you're curious, check out letsgetrusty.com/startwithabstraction or click the link in the pinned comment below this video. Now, let's get an overview of the main steps a compiler takes to translate source code into machine code. Each of these steps will get its own video, where we go into depth and look at concrete examples. The first step is lexing, which transforms the raw characters of the source code into a sequence of meaningful tokens, removing unnecessary whitespace and comments in the process. These tokens are then transformed into a so-called abstract syntax tree, or short AST, in a process called parsing. Here the compiler checks if the source code matches the syntax of the language. On the AST we can then do semantic analysis, such as name and type checking. Next, the AST is transformed into an intermediate representation, short IR, which is not tied to any particular input language or target machine. On this IR, it is particularly easy to perform optimizations such as dead code elimination or constant folding. Finally, the compiler generates actual machine code, which includes, but is not limited to, determining the order of execution, choosing instructions from the instruction set, and assigning hardware registers. Note that modern compilers have even more steps, which I will brush over for simplicity. These steps are usually grouped into three broad stages: the front end, middle end, and back end. Thinking about a compiler in terms of these stages has quite a practical advantage. Let's say we want to compile the same source code to multiple entirely different hardware architectures. It would not make sense to write a whole new compiler for each one. Instead, we can reuse most of the compiler and just swap out the last part. There are several projects out there that standardize these layers. For example, Antler can generate lexers and parsers given a formal grammar of your source language, and LLVM handles the middle and backend parts. This has obvious advantages, as optimizations on shared IR will be similar for many source languages. And writing a parser is tedious and can actually be automated, so it makes sense to do that too. But there is not much fun in just stitching together what others have built, so we will see how to do everything from scratch. There are even other procedures that are commonly done or even necessary before the code can run, but depending on who you ask, they are not part of the compiler. These include preprocessing, which performs code substitutions and inclusions. After the compiler has created the machine-specific assembly, it must still be mapped to the corresponding zeros and ones for the computer to execute, which is called an object file. Finally, a linker combines multiple such object files into a final executable. Now, let's return to the question from the beginning. How is it even possible for a compiler to be written in the language that it compiles itself? Sure, we could write it in a different language, say, write a Java compiler in C first. But then, where does that C compiler come from? What we are talking about here is so-called bootstrapping. Let's imagine we're the first people to ever write a compiler for a language I want to call Lace. We want our language to have all sorts of cool features like if statements, variables, loops, constants, type inference, classes, modules, pattern matching, metaprogramming, syntactic sugar, and a big standard library. But we don't actually need all of those features just to write a minimal compiler once. So we strip our language down to a subset that is as small as possible, but still expressive enough to write a small, inefficient compiler in it. Let's call it version 0 of Lace. Then, we write a compiler that can compile the subset of the language. Since we don't have a compiler yet, we have to write this first one in actual executable machine code. This can be quite tedious and error-prone, but we just need to get something that roughly works. And because we are only implementing a small subset of the language, the workload is manageable. Then we can use this bad compiler to write a slightly better compiler. Still inefficient, but capable of compiling the full language in all its glory, version 1 of Lace. And once that's done, we can use the full expressiveness and feature set of our language to write a perfectly optimized compiler. Of course, we can do as many steps in between as deemed necessary. Last, a small word on compiler design. Compilers are a unique kind of program. They have very strict requirements. First, correctness. A compiler must always produce code that is semantically equivalent to the source, behaving exactly as defined by the language specification. Any bug in a compiler can cause serious problems down the road if it introduces bugs into every program it compiles. Next, language compliance. A compiler must accept all programs that are valid according to the language specification and reject those that are not. Usability has also become an important aspect of modern compilers. Developers expect a compiler to be fast, even on huge code bases, and to provide meaningful, helpful error messages pointing out the erroneous locations in the source code, ideally with suggestions for fixes. Finally, compilers are expected to behave deterministically. The same input should always produce the same output. But it goes even further than that. For example, Linus Torvalds once said that he likes C because he knows exactly what assembly will be generated from it. The goal of this series is to show you that, in principle, you could write a compiler for your own language. But if you want to do serious compiler development, you should still pick up a proper book on the topic. This is a good time to mention the so-called Dragon book, which is probably the most famous book on compilers. I will cite it often throughout the series and show many examples from this book. It is also written in a very approachable tone, so you may very well pick this one up if you're interested. Generally, compilers aren't conceptually that hard. They just can be a lot of work. It only becomes a hard topic when you want them to be efficient or bug-free. So if you want a challenge, try it. One more thing, I just launched a Patreon. So if you want to support this series and help me make more videos like this, the link is in the description. This has been Premature Abstraction. Thank you for watching.